let's continue looking at that basic common source configuration. So previously we had analyzed this common source circuit, or we had done our DC analysis, and we had found that our IDQ was approximately equal to 0.174 milliamps. So the next step in our process is to calculate our small signal parameters. So we know that our GM is equal to 2 times the square root of Kn times IDQ. So we plug in our values, so we had that our Kn was given here in the problem statement as 0.5, and our IDQ we calculated to be approximately 0.174. So if we plug all that in, we get that our GM is approximately equal to 0.590 milliamps per volt. The second parameter of interest when we're doing our small signal analysis is our small signal output resistance, R0. We know that's equal to 1 divided by lambda times IDQ. And this is going to be approximately equal to 1 divided by our lambda, which also was given in the problem, of 0.02, times our 0.174, our Q point drain current. And we get that this is approximately 287 kiloohms. Okay, so with these parameters, now we're ready to do our AC analysis. So let's go ahead and draw our small signal equivalent circuit. As always, we can start by drawing our gate, our drain, and our source terminals. We know that between our gate and our drain and our gate and our source, we don't have anything. It's an open circuit, and we're interested in this gate to source voltage. Between our drain and our source, we have a dependent current source with current going from the drain to the source, and the value of that current is GM times VGS. We also have that small signal output resistance R0 between our drain and our source. So this is lowercase r0. So that is our transistor. So now to draw the rest of the circuit, we need to come back to our configuration here. And so remember that when we're drawing that small signal equivalent circuit, we've shorted out or deactivated our DC sources. So more general would be to say we deactivate. So because we have a voltage source here, we would short that to ground for our AC equivalent circuit. And so what that means is we can see we're going to have from our drain RD going to ground. From our source, we are also connected to ground. So let's go ahead and draw both of those things. So we have our source is grounded. We have our drain is connected to ground through RD in the external circuitry. And we also have that output voltage was defined at our drain. So with respect to ground, we have this V out here, and we notice that's still equal to VDS. We also are going to have our drain current defined right here. So this is going to be our ID. And let's come back and take a look at our configuration at the gate. So looking at our gate, we see we have a couple paths, or rather a few paths to ground. So we have a path to ground through this R1 resistor. We also have a path to ground through this R2 resistor. So we can say we can go to ground through either of those two, which are in parallel. So let's go over here, and we can say between our VG, or not our VG, but between our gate and our source, we have this resistance of R1 and R2 in parallel. So also between our gate and ground, we can go through this coupling capacitor, which remember is going to act like a short circuit to AC signals. We go through RS1 through VI to ground. So let's add that down here as well. So we're going to have some RSI right here. And we're also going to have our input, V sub I. This was RSI. And that's connected between our gate and ground. And so again, remember our transistor is just going to be everything inside of here. So it includes that. Let me do that a little better so I can include our small signal output resistance. And then everything external to that highlighted loop comes from our particular circuit. So let's define a couple of other things. So again, keeping in mind that highlighted loop, we can define our input and output resistances. So looking into our amplifier, so basically what our AC source input is seeing is going to be our input resistance. So this is going to be defined as Ri looking in at that dashed line there. Our output resistance is going to be looking in from the output. So our output resistance is defined as looking in to that dashed line there. We're looking in at the drain terminal. So now we're equipped to further investigate some of these parameters, our AV, our RI, and our R naught. So let's start by looking at our small signal voltage gain, A sub V. So let's find an expression for A sub V. And so of course, remember in general, that's going to be V out over VI. So let's start in the same manner that we did last time by looking at our output loop over here. We can see it's the same exact thing we saw last time. Actually, we're going to have this R naught and RD, which we can combine in parallel. And then we have this current GM times VGS, which is going upward. So that creates a voltage drop, which is going to be of an opposite polarity of this output voltage. So what that means is we can write our output voltage, V out, is equal to negative GM times VGS. So that's the current in that dependent source, times R naught in parallel with RD. Okay, so now what we want to do is look at our input side and relate that VGS value here back to our VI such that ultimately we can find this ratio of V out to Vn. So from the input side, we see we have a simple voltage divider, so we can say our VGS is equal to our VI, our input voltage, times RI in the numerator divided by RI plus RSI. And so of course what we can see from that is our RI is just going to be our R1 parallel with R2. And so we'll come back to that in just a second though. So let's just combine these two equations. So we're just going to take this expression here and plug it in for our VGS, divide through by VI to get our voltage gain, A sub V, which is equal to negative GM times R naught parallel with RD. So let me clean that up a little bit. So R naught parallel with RD, and then we have that voltage division. So we have RI divided by RI plus RSI. Okay, so that would be our voltage, small signal voltage gain. So what exactly is that RI? So like we said, our input resistance, because our input resistance looking into the gate, so if we look in here, it acts like an open circuit, so we say that would be infinite. So anything in parallel with infinity is just going to be whatever that thing is in parallel. So in this case, just the R1 and R2. So we can say our input resistance, R sub I, is equal to R1 parallel with R2. And so that checks out based on our summary table where we said the input resistance was based on our biasing network resistors, our Thevenin equivalent as we called it. So the last thing that we want to look at is our output resistance, R naught. And so we can use a similar method as we used in previous analysis for our BJTs if we do a test source. So we can do a test source at the output to find our output resistance, uppercase R naught of the amplifier. And so the basic idea is we can have either a voltage or a current. Really doesn't matter, and at least in our paper analysis, of course, if we're doing this physically in a lab or in some physical setting, of course it will matter. But we say we have some test voltage V sub t, which creates some test current I sub t, and then we use the ratio to figure out our output resistance of the circuit R naught. And so really we don't necessarily even need to draw that circuit, because remember when we do this method, what we have to do as a first step is to deactivate independent sources. So deactivate our independent sources. In this case, there's only one of them, that's that small signal input V sub I. So if we deactivate the V sub I, we're shorting it out, which means it's going to be 0. So if we deactivate that, we have VI equals to 0. If our VI is equal to 0, from this equation up here, we see that means our VGS is also equal to 0. And if our VGS is equal to 0, then of course anything times VGS is also equal to 0. So that means our current here is equal to 0. And so if we have a 0 current there, that's essentially just an open circuit here. And so that means the only thing we really have left is this R naught in parallel with RD. So we can say then that our output resistance is going to be R naught in parallel with our drain resistance, RD. And so here we see, as we saw from the summary table, this is going to be typically dominated by this RD value. And the reason is because oftentimes that's going to be smaller than the lowercase r naught, which means it's going to dominate that parallel combination. So to get a better feel for that, let's plug in some of the exact values, because remember, we actually have GM and lowercase r naught values for this circuit from the parameters we had in sort of the previous video as well as the slide above. So plugging in values for this particular system, we would have an input resistance, which is equal to the parallel combination of R1 and R2. And so we see that's about 42 k ohms. Our small signal voltage gain, if we plug into that equation, we get approximately negative 5.21. Keeping in mind, of course, we sort of approximated our IDQ to get that GM value. So it's not quite as accurate, but it was definitely easier to calculate. And then finally, our R naught value, we expect it to be dominated by RD. And sure enough, we see if we do that calculation, it comes out to be 9.66 k ohms, which is just a little bit smaller than the 10 k ohm RD. And so, of course, that 10 k ohm is much smaller than our 287 k ohm of our lowercase r naught. And so, of course, keep in mind that these equations are for this particular circuit. If we adjust this circuit a little bit, we will have to either adjust these equations or go back and resolve them if we have significant changes. The other thing to mention too is, of course, when we have this sort of non-ideal input resistance associated with our source, we're now having to consider our loading effects again. And the same would be true if we added some load resistor at our output here, R sub L. We would have some loading at our output. And so that goes back to the discussion we had when we were talking about BJT amplifiers. And of course, everything we said there is going to be true as well here for our MOSFET amplifiers.